cover trigonometric integrals. So we can use trigonometric identities to actually integrate certain combinations of trigonometric functions. So let's look at this example. Let's say we're told to evaluate the cosine of x cubed with respect to x. Okay, so we're looking at an integral with an odd power of cosine x. So we'd like to use the substitution rule, but if we were to substitute u, what is it, u is equal to cosine x, that really wouldn't be too helpful, since we would take du, right, and that would equal to the negative sine x dx. So not much help there, because in order to integrate powers of cosine, we would need an extra sine factor. Similarly, a power of sine would require an extra cosine x factor. So here, we're going to separate one cosine factor and then convert the remaining cosine squared x factor to some expression involving sine, right? And we're going to use the identity that we're familiar with, the identity sine squared x plus cosine squared x is equal to 1. Remember that? Okay, so if we have cosine cubed x, we can say that's equal to cosine squared x, right, times cosine of x squared x times cosine x. All right, so if we go further with this, remember we can use that identity right up above, right? Cosine squared x, so we can rewrite it as 1 minus sine squared x, right? And then multiply times that cosine x. Okay, so then we can evaluate the integral by then substituting in, okay, u is equal to sine x, right? So therefore du is going to be cosine x dx. All right, and now I'll just rewrite it over here. The original was cosine cubed x dx, right? The integral of that. So in writing this over, now we can say we have cosine, I'm just going to write it all over. Cosine squared x, integral of that, times cosine x dx. And then it's going to equal to the integral. I'm just writing it over with the integration symbol, right? But we had already shown above how we can make this substitution. 1 minus sine squared x times cosine x dx. Okay, and then when we substitute, we're saying that u is equal to sine x, right? U is equal to sine x. So we substitute. Now we can do substitution. So we have the integral of 1 minus u squared. So sine squared x is the u squared. And then we have du, because we said du is cosine x dx, right? All right, so now this makes the problem easier for us. We can go ahead and complete this integration, because we know that the integral of some constant with respect to u is going to be u minus, and now we use the power rule for integration, so we'll just add 1 to the exponent to get u to the third, and then you also write that number down in the denominator plus our c, our constant of integration. All right, and then we can say, okay, let's have u now back sub to make it sine x, right? So u is sine x minus, and this u to the third over 3 is like 1/3 u, right? So I can write the 1/3, but u is sine, and to the third power, so sine cubed x, and then plus c. All right, so in general, so this is it for us. That helped us out a lot, tremendously, right? So in general, we try to write an integrand involving powers of sine and cosine in a form where we have only one sine factor and then the remainder of the expression in terms of cosine, or only one cosine factor and then the remainder of the expression in terms of sine. So it looks like the identity that we're using, sine squared x plus cosine squared x equals 1, right? That identity that we learned a while ago in back in pre-calc, that enables us to convert back and forth between even powers of sine and cosine. So sometimes if the integrand contains only even powers, right, of both sine and cosine, if it just contains only even powers of sine and cosine, then there might be a problem. That strategy fails a little bit. So we're going to have to take advantage of other identities we know. So do you remember this one? Half angle identities, right? It'll all come back in a second. Half angle identities. So this was sine squared x is equal to 1/2 1 minus cosine 2x, right? Call that one. And then the other one was cosine squared x is equal to 1/2 times the quantity of 1 plus cosine 2x. All right, these were the two half angle identities that we've dealt with. All right, so next, what I want to look at is an area for us, and this area is trigonometric substitution. Trigonometric substitution. All right, so let's take a look. So a number of the practical problems require us to integrate algebraic fractions that contain an expression of the form square root of a squared minus x squared, or something like a squared, the square root of a squared plus x squared, or even something like x squared minus a squared. All right, so again, some of the practical problems actually require us to integrate algebraic functions that contain an expression of one of these forms. So sometimes the best way to perform the integration is actually to make a trigonometric substitution that gets rid of the root sign. So again, sometimes the best way to perform the integration is to make a trig substitution that gets rid of the root sign. All right, so let's give this a try. That the area of a circle with radius r is pi r squared. Okay, so to keep it simple, we're going to place the circle with its center right at the origin of our Cartesian coordinate system. So the equation, as we know, is going to be x squared plus y squared is equal to r squared. All right, so then if you solve this equation for y, carry out the algebra, you should get y equals plus or minus the square root of r squared minus x squared, right? And then because the circle is symmetric with respect to both axes, then the total area is 4 times the area in the first quadrant, right? If you can look at the figure, you'll see what I'm talking about. Okay, so the part of the circle in the first quadrant is given by the function y equals the square root of r squared minus x squared, right? Because it's in the first quadrant. So therefore, we have 1/4 of the area is equal to the integral from 0 to r of the square root of r squared minus x squared with respect to x. All right, so next, to simplify this integral, we're going to make a substitution, right? We're going to make a substitution that turns r squared minus x squared into the square of something. We're going to turn this into the square of something. So the trigonometric identity of 1 minus sine squared theta equals cosine squared theta. This is going to be useful for us here in this situation, right? In fact, because r squared minus r squared sine squared theta is equal to r squared times 1 minus sine squared theta, right? Which would give us r squared, and then we'll have cosine squared theta, because 1 minus sine squared theta is cosine squared theta. Okay, so then we go ahead and make the substitution. X is equal to r sine theta. X is equal to r sine theta. So we make that substitution. So from this, since, let's pull it up some, since x is between 0 and r, we restrict theta. We restrict theta. We restrict theta so that theta is between 0 and pi over 2. So we have dx is equal to r cosine theta. So we had x is equal to r sine theta. Now if we find dx is r cosine theta with respect to theta. Okay, and then from this we can say, okay, r squared, the square root of r squared minus x squared, square root of r squared minus x squared. That's going to be equal to the square root of r squared minus r squared sine theta. R squared minus r squared sine theta. Okay. All right. And then in our next step, we can go ahead and write r squared instead of what we have before. We can just write r squared cosine squared theta. So this is going to equal to r cosine theta, taking the square root of it. So because, let's say because cosine, let's write it out, because cosine theta is greater than or equal to 0, right? It's greater than or equal to 0 when 0 is between 0 and pi over 2. So cosine is greater than or equal to 0 when, I'm sorry, theta is between 0 and pi over 2. Alright, so then thus the substitution rule gives us from 0 to r, we have the square root of r squared minus x squared dx. Alright, so I'll write it under here, equals from 0 to pi over 2, we have r cosine theta, okay, times r cosine theta with respect to theta. Okay, so now if we take it further, we'll have r squared to pull out from 0 to pi over 2. Take the integral of cosine squared theta, right? Just from the multiplication of the line above, and then pulling out the r squared as a coefficient. And then this is with respect to theta. So this trigonometric integral is similar to the probably other ones that you worked with. So it's probably similar to one that we've done as well, right? So we're going to integrate cosine squared theta by means of an identity, right? So if we have cosine squared theta, that's equal to 1/2 times 1 plus cosine 2 theta. So we can do that. Integrate by means of an identity. Okay, so therefore the 1/4 a is equal to r squared from 0 to pi over 2 cosine squared theta with respect to theta. Okay, and then that's going to equal for us 1/2 r squared from 0 to pi over 2 1 plus cosine 2 theta. 1 plus cosine 2 theta, right? So we said that we were going to integrate by means of the identity. So we're using the identity here to help us integrate. And this is with respect to theta. And then we have 1/2 r squared. All right, so we have the integral of 1 will be theta plus the integral of cosine 2 theta is going to be 1/2 sine 2 theta. And then we're going from 0 to pi over 2. Okay. All right, and then next we'll say 1/2 r squared. And then we have pi over 2 plus 0 after just substituting in, right, the limits of integration minus 0. And then we're left with 1/4 pi r squared. So given all of that, we have proved the famous formula a is equal to pi r squared.